Hello YouTube, De-bodgery here. Welcome to EV Components Review. This is an introduction video to a new VESC player, or the way they describe themselves is EV supplier or EV component supplier, of which their first products on the market is two controllers. So as you can see, their name is Seven, all in capital letters with a backwards E, and it's really 7 electric cents. Um, and for now, they're going to have two controllers that they're going to be releasing pretty soon. Um, I can only show you some pictures of things. There's things they don't want me to show you about everything, so I don't have that, or I just simply don't have pictures of certain things. Um, but anyway, 7 electric cents is this company. They have never released anything before. I know the engineer. I've talked to him many times over the years. Very, very smart guy. He understands all the things that you hear me harp about bad designs, and doesn't make those kinds of design choices because he knows better. So yeah, as far as his designs in these controllers, I definitely like his work. There are tidy, well laid out, efficient current paths, capacitors in the right places, things like that. So anyway, this is a mock-up of the 718, in a 3D printed case. This isn't how the thing's really going to look at all. Yeah, this is just something that they had because, well, their shells are, still getting designed. They have watched my videos many times, which is why they reached out to me to tell me to show them off, so I could tell you about them. But they said, if you like some of those other cases that you've seen before that you've raved about, you'll definitely like what we're going to do. They're going to be super sexy as well. So anyway, yeah, I'm going to assume that they're going to be super sexy until I see them and like, oh my God, I really, really love this the most now. I don't know. Can't say because, that's all I really have to go on. Anyway, I don't have pictures of rough draft shells or anything like that. So all I've got closest thing is this. And this is physically the same size of a typical smartphone. Yeah, this is a very tiny little controller. And I'll talk about the specs of it after a little bit when we get inside to look at the board. Um, so this little opening right there, that's where the I/O board plugs in, and I'm assuming it's got like JST connectors on it or something. But yeah, that's where you're going to plug in. And also on that little I/O board, there is the VESC Express mounted on that as well. But anyway, I'll show that some more in detail when we see the next picture. Anyway, yeah, this is the 718, and it's about the size of a typical cell phone. They showed me a picture of it next to an iPhone 12, and it was physically, the board itself was physically the same size as an iPhone 12. All right, so here is the actual board. And yeah, you can see that connector, that pin header right there. And so that I/O board will plug in there. They are apparently working on a couple different versions of it. I don't know what that means per se, but yeah, that's what they told me, is that they've got a couple different versions of that I/O board. But yeah, the ESP32 or VESC Express will be stuck to the bottom side of that, plus a whole bunch of connectors. I'm assuming there's also a USB-C port on it as well for the VESC Express, and this one here is for the CPU. Anyway, let's look at this board. What we can see, these are on-semi gate drive chips. These are all Nichicon electrolytic caps. I know that because they told me that. You can't really see it on the parts. You can see that they are 100 microfarad and 160 volts. And on the 718 and the 730, oh, and I guess I should say that too. So yeah, they call everything 7 dash and some number. 7 being the company, 7 electric cents. And then dash 18 indicating 18 MOSFETs, 7-30 indicating 30 MOSFETs. So yeah, that's how their naming convention works. All right, so anyway, as you can see, these are tall MOSFETs, and they are mounted to the top side of this multi-layer printed circuit board. And I'll show you this after a while when I get there. But under each one of these MOSFETs is a gazillion little teeny tiny vias for current and heat transfer. There's a couple different companies doing this where they use tall MOSFETs and multi-layer printed circuit boards. and many vias to transfer heat and current. And 7 is doing the same thing. The first one that comes to mind is Trampa has done that for years. Of which their latest offering is actually tall based is the STR 500, and it's doing the exact same thing as this is. So perfectly viable way to use the tall package without needing a metal core printed circuit board, using a multi-layer printed circuit board instead, which gives you a lot more design flexibility. And you don't need to have copper reinforcing because you literally do it with many layers inside the board. ASI does that as well, many layers to do the copper reinforcing rather than having to add surface copper reinforcing. And these guys are as well. So anyway, here is your main 12 volt DC to DC, and they are kind enough to silk screen on the board what it's capable of, 4 amps, 12 volts. So yeah, super cool. You can get 4 amps out of this thing. So I'm assuming that they're going to want to use this for, like, I don't know, powering an external fan or water pump or something as well. Whatever you want to use that 12 volts for. Here is your 5 volt DC to DC converter. And over here is your 3.3 volt linear regulator. In fact, you can even see it on that one. Yeah, see it says TL33 on there. Yeah, that's because it's a 3.3 volt linear regulator, and it's basically for providing power for the STM32F405 and yeah, maybe for the ESP32, something like that. All right, so something else I want to show you here before I moved on. I completely lost my train of thought. Oh yes, this right here. Okay, so kind of two things here. You'll notice these studs, they're round and they're soldered down to the board. As soon as I saw that in the pictures, I said, so that, studs like this, they twist off. And, I've talked about that and repaired it on KO controllers. I've talked about it and repaired it on ASI controllers. In fact, I have an ASI BAC 8000 in my possession right now for that very problem. And I mentioned that to them. They went, oh, wait till you see how we do our studs. We think it's going to be really strong. Anyway, solder isn't that great for resisting twisting forces, and it breaks loose, and then your studs come off, and then the current between the stud and the solder pad just burns all that away, and then you don't have a current path anymore. In which case, repair is much more difficult, which is the problem I have with the BAC 8000 in my possession right now. All the solder pad on the board is completely destroyed, and I've got to rebuild it. Anyway, these guys have a plan in mind, which I'll talk about when I get to the bottom of the board. I just wanted to point out that they're using these studs and that they're soldered down, and I'll talk about that some more in a minute. All right, so the key thing here is they're kind enough to silk screen on the board. There are 3 voltages, 100 volt, 120 volt, 150 volt, and this is true for the 730 as well. But yeah, 750, 600, and 500 amp peak, and 520, 270, and 200 amp continuous. The only thing that's different between the 3 voltage versions of the 718 or the 730 is the MOSFETs. Otherwise, everything else is all the same. So if you bought a 730 100 volt and you wanted to change that over to a 730 150 volt, swap out the MOSFETs and you're done. Yeah, same thing for the 718. Swap out the 100 volt MOSFETs for the 150 volt MOSFETs or whatever. And now you've got the other voltage range. So anyway, yeah, for a controller that's literally the size of a cell phone, this is pretty damn powerful, folks. This might be the most power dense controller I have seen yet. Yeah, 3 MOSFETs in parallel, so if we assume these are like 300, 310 volts each, that's 900 amps, maximum. And then we're rating it for 750 amps peak and 520 continuous. Okay, I can buy that. All right, so let us look at the other side of this board, because I have a picture of the bottom side of the board. It's pretty boring, but there's stuff to see nevertheless. Definitely like having all these electrolytic capacitors crammed right up next to the MOSFETs. Oops, and I forgot to mention something about this. Yeah, this is going to keep the noise around these MOSFETs, because this is the noisy section of a power stage, or of any controllers, right around the MOSFETs. It's going to keep noise down a lot, because these guys are smack up against all of the MOSFETs. There is no chance of noise getting out of here and getting over here or anything like that. This is going to mitigate any DC bus noise or AC noise a great deal. There's some ceramic caps here, here. There's some in there. You can't see it. They're over there. And there's some back over there as well. So there's ceramic caps kind of spattered all over the place between the MOSFETs and in between the phase buses and things in here as well for high frequency stuff. We've got 3 linear holes right here. So you have a current concentrator ring that'll sit over top of each one of these studs. And then the gap in those will be right around those linear holes for measuring phase amps. All right, let's look at the bottom side of this board. Pretty boring. Not a whole lot to see. 7 electric cents. Probably the biggest thing I want to show you is all those little itty bitty vias, because the bottom side of this board is pretty boring. There's nothing here. You can see where the linear holes are soldered in. You can see where the caps are soldered in. That's kind of it. Almost, right? But we zoom right on in. That's probably better right there. Yeah. So you can see all those little tiny pucker marks in there. And that is little vias that pass from the top side of the board where the MOSFET is soldered down through all the internal copper layers that are current path as well, all the way down to the bottom of the board, tied all together. So all those little vias, they act as a current path, and they also act as a thermal path. It's copper. It's going to do really good at that. And so like right there, you're looking at a whole phase. That's a phase bus right there. And it's tied together with internal copper, plus all these little vias in here, things like that. And then that brings me to the other thing. There's a better picture. There we go, that one. So, I was telling you about these studs, and you can see that they're threaded inside. So that stud is actually hollow all the way through, threaded all the way through for M6. And they are going to put an M6 screw right on top of here. Whether they solder it in place or whatever, I don't know. But yeah, they're going to literally secure those studs to the board with an M6 screw on top of it being soldered in place. Without that screw in there, this is basically the exact same implementation that ASI does, with just trusting solder to do the job. And their studs definitely twist off. So that screw is going to definitely add more support and security and reinforcing over just solder by itself. I don't know if they're going to use Loctite or whatever else in there to hold that all in place, but yeah, the screw is definitely going to add more support for keeping those studs from twisting off or breaking off. All right, so you'll notice there is this bare piece of copper across here, so that's effectively battery plus across there. And then you've got this bare piece right there, that's a phase, that's a phase, and that's a phase. Battery minus, which isn't really exposed here very much. There's a little bit of it right there, but it's not bare. So battery minus bus would be right across this area right here. But the reason why these are bare is so that not even the solder resist interferes with heat transfer out of the underside of the tall MOSFETs. You see those little pucker marks in there. That's all those little vias. So, really good thermal path from here through thermal gap filler to some kind of a raised section in the shell that touches on the other side of the thermal gap filler to be the thermal path to the heatsink. And so there'll be something along here and something across here with some notches in it around those 3 linear holes for your thermal path out of this thing, to the shell, which is the heatsink. So anyway, these are far from the first time I've seen something like this. The STR500 does it this way. Tramp has been doing this kind of design for a number of years, where they, put the MOSFETs like on the top side of the board, many vias, and then transfer heat out the bottom side. Use copper in the board as your current paths and just many layers of copper tied together with many vias, so you get plenty of current path. And 7 is doing that as well. So it's a very acceptable way to get enough copper to be able to make nice, stable, beefy phase buses and battery buses and things like that. You don't have to use copper reinforcing. And it also lowers your cost and your assembly cost because it's all built in. There's no part to add. And that's not necessarily a bad thing. So anyway, that's the, oops, didn't want to move on. I want to go back there. So that's the 718. And then 7 electric cents, they also have this, and this is the 730. I don't have pictures of the bottom side, so I can't really show you that, But this is tall T based, and like the 718, it's all Infineon MOSFETs. It's all, you know, name brand components everywhere. The biggest difference as far as parts are used between this and the 718 is this isolated DC to DC converter, tall T versus tall. You know, these are on semi gate chips. Everything else on here is pretty much the same. You've got Molex connectors and these little hall boards, which I'll talk about. Otherwise, everything else is almost exactly all the same parts. Just, you know, bigger board. And this board is about the size of like your Samsung, you know, tablet type phone. So a little bit bigger than, you know, like a standard, you know, smartphone, but still a pretty small form factor. Yeah, I can't show you the bottom side, but the CPU sits underneath here. There's a linear reg and a couple other parts there as well. I've got other pictures of this. Anyway, these caps, you notice they got gaps between them. They couldn't get the ones that they wanted, which are slightly higher capacitance to fill in those gaps, so the caps are all kind of bunched together more. But these are still 330 mic caps, and there's a whole bunch of them. So there's plenty of capacitance here. And they also have added some ceramic caps on here as well. In fact, let me just go to a more overhead view. There we go. Of those ceramic caps. I'm guessing, but you'll notice they've got a bunch of them here and a bunch of them here, but there's none here at the center face. But the gate chips are right there. I'm guessing that the reason why they don't have more ceramic caps right there is because they just simply ran out of real estate for circuit traces and things like that to be able to put more ceramic caps in. Thing is, though, is they have a whole bunch of them, and they are still all around the MOSFETs, so probably this is still going to be a pretty tidy and clean for high frequency noise setup. Yeah, it would have been kind of cool if there was some in there too, but you know, design choices oftentimes limit what you can and can't do, and that's probably why they didn't do them there. They literally didn't have the real estate to be able to put more ceramic caps right there. I'm guessing. These little guys right there, these are resistors. And since there's 5 of them in a row right here, and there's 5 more up there, there's a pretty much 100% chance that's your current limiting resistors for the MOSFET gates, which are on the other side of the board. I'm going to say there's a pretty damn good chance of that. All right, so let me talk about these little boards right here. This is a clever bit of kit, which I like a great deal. I'm going to zoom on this one first so you can kind of see it. All right. Yeah, and you can see some of it. So this little piece right here, this is a surface mount Hall IC. It's not just a 3-legged part. It's a chip. It's got like 8 legs on the thing. I don't know what else those other ones do. Didn't look up. Don't know anything about the part, so I can't look it up. But yeah, it's a linear Hall on this little thing. This little gate, a little linear Hall IC rather than just a Hall. And it's stuck into the copper. So, you know, this is your phase bus right here. It's vertical, you know, not horizontal. This is perfectly acceptable. There's a design that I'm working on that uses vertical copper rather than laying it down on the board so that it takes up less real estate on the board. And that's a good thing. So yeah, electrons don't care that they flow through a vertical thing or horizontal thing. They literally don't. So this is perfectly acceptable to do it this way. And this makes their phase bus much smaller, you know, as far as, you know, real estate on the board. Anyway, yeah, so they've done a couple little clever things here. So that linear Hall is right there, and then they've got like a couple capacitors and other parts on here, and that's all about cleaning up induced noise. Phase buses, surprisingly enough, like I've never said this before, can be noisy. And they can induce noise onto your current sense electronics and make them noisy too. So yeah, they've cleaned that all up on this little board, and according to them, this is a pretty tidy little way to be able to measure phase amps and to get really reliable readings that are very, very low error and low noise. However, right here you can see these three holes. That's so you could put a current concentrator ring around here and use a linear Hall as well. Could use either one, but according to them, this little board is a lot better. And that little Hall is stuck in a slot in this piece of copper. And then I'll show you a different one here so you can see these a little bit better. So here's the next phase over. Yeah, you can see these little slots in here. and there's like a little piece of copper web right there. And effectively what that does is it focuses the inductance of current flow through this thing to right around the linear hull. You can see some of its little legs sticking out right there on that linear hull. So it focuses the inductance that's created from current flow in that copper right at the linear hull, so they can get a really good current reading. But yeah, no current censoring, no shunts. Completely different way of measuring phase amps than I've ever seen anybody ever do before. I like this. This is very clever. I like the very low real estate usage of this vertical piece of copper. Yeah, all of that is very cool. And on top of that, this isn't the only copper for the phase bus either. You've got many layers inside the board. The bottom side where the tall T MOSFETs are, there's more copper there as well. So yeah, this isn't the only copper for the phase bus. There's more. This is a multi-layer printed circuit board after all. All right, so they pointed this out to me, and that is that these controllers, they can't operate at less than 40 volts, and it's because of this isolated DC to DC converter used for powering the high side gate drive for the MOSFETs. And as you can say, input voltage is 40 volts to 160 volts. So this is the limiting factor right there. So you can't run these controllers at less than 40 volts because of the isolated DC to DC converter for the high side. Why you'd buy a controller like this and then run it at 40 volts is an absolute mystery to me. But yeah, that's your bottom line, your bottom limit rather. And it's because of this isolated DC to DC converter. So yeah, don't try to run these things at less than 40 volts because they won't power up. Okay, I think that's probably everything, almost everything I want to show you. One last little detail, I guess. So you see this silkscreen rectangle right there, and you can see another one right there. The tall T MOSFETs are plunked down right underneath those two spots. And then their legs solder right down, right next to these pieces of copper. So as far as, phase buses are concerned, they're very tidy, very tight. Obviously, I don't have a picture of the bottom side, so I can't show you that. But also, right across here on the other side of the MOSFETs, that's your high side copper, and there is added copper on there. And right there's the battery plus through hole for the wire. And then battery minus is, again, there's some surface copper plus all the layers inside the board. That goes right across there. And then there is your through hole for battery minus. And that's where the battery minus will solder down. What size those wires are, I don't know. They didn't tell me. I'm going to guess, like, say, 6 AUG, something like that, considering that this is going to be one hell of a horse. Yeah, this is going to be a beefy controller. If they, I don't see a silk screen on here, and it's not on the bottom side of the board either. That tells you those same kind of specs like you see on the 718. But considering that this is tall T, 30 MOSFETs, it's probably going to be something like double the amperage of the 718, or pretty darn close to it. So yeah, pretty powerful thing in the physical size of your tablet phone. Well, very, very compact, just ridiculous amounts of amperage in a really, really, really compact form factor. All right, folks, I think that's everything I've got to say about this. Be looking forward to 7 electric cents hitting the market sometime soon. Both of these controllers are in the hands of testers right now. Yeah, so they're actively testing them. There's details to work out, more logistics kind of a thing, shells, what that might end up looking like, a few other things like how they're going to connect to these phase buses. I don't know what that is. Something bolts on there. I just don't know what. A few details like that, but otherwise these controllers are actively being used by testers right now, so they should be seeing just those few little cross the T's and dot the I's stuff done, and then we see them hit the market. Anyway, yeah, 7 electric cents, new company that's never produced anything, and I like what they're doing. Good designs, nice tidy phase buses, nice tidy battery buses, put all the capacitors in the right places. and not have to spend a lot of money on the design of the thing, you know, with extra copper and, you know, multiple boards and things like that. Just do it on a multi-layer PCB. Put the copper where you need it. Put everything all nice and tightly together, so you don't need a lot of extra copper. You know, that's added copper to the surfaces because you do it in layers in the board. So you only need to add minimal amounts to be able to pull off the same result because it's all otherwise in the board. And so, yeah, that's kind of Seven's mentality, is to try to make it as tucked in and no extra anything that you don't have to have because you don't need it as possible. Don't mind this design at all. This has been done similar things like this before, and it's a perfectly acceptable way of doing things. So anyway, folks, look forward to 7 Electric Sense being on the market sometime soon. As far as I know, they don't have a website yet. At least I didn't find anything. I'm sure that's getting propped up just as quick as they can, because, you know, these guys were focused on designing these controllers so they can get them on the market as quick as possible. They also have a couple other things in the works that I only know a few details about. They have a 400 volt VESC controller, and I'm going to assume, they didn't tell me this, that it is going to be silicon carbide or SiC-FET based. That's the best choice. IGBTs are not really it. SiC-FETs are much a better option. So 400 volt VESC, that is SiC-FET based, is probably what that is. Specs, don't know. How big it is, don't know. Don't know what it looks like, don't know. They also mentioned that they have a all CNC machined aluminum full grip throttle. So and it's forward and backwards rotation. So you twist it backwards and you get throttle, twist it forward and you get variable regen. So you know, all right-handed control and a full grip twist throttle. And of course VESC supports throttles like that. So yeah, it's supposedly got bearings in it, so it's super silky smooth, you know, operation. But yeah, single throttle, forward and backwards twist on the thing for a variable regen and for throttle. You know, all right-hand control. Yeah, when I do variable regen, which I do, I use 2 throttles, left hand and right hand. And here they're building something that's all CNC machine, that's all right-hand control. So yeah, that should be super cool. I don't know what else they're doing. They didn't say, but they said they have other things in the works. They're not just doing controllers. They're doing other things that are EV related. And clearly they're, you know, considering the power of their stuff, they're trying to hit kind of the motorcycle world, is the way I see it, you know, considering the power output that their controllers have. Yep. Anyway, folks, welcome to the world, 7 Electric Sense. Hope to see more from you. Hope you guys make it. Yeah, I like what you're doing so far. Yeah, your designs are definitely very tidy. They're very tight, really compact, really power dense. Yeah, I hope you guys make it. Man, you guys got some good potential here. And definitely you chose the right thing, VESC. Good job. Double thumbs up for that one.